All right, the next section on oxygen nucleophiles is relatively long, so I've broken it up into a couple parts. All right, the first example we're going to consider where oxygen is nucleophile is the formation of hydrates, where we're essentially adding water. Right, we're starting with this ketone, and then we're adding an oxygen and two hydrogens, so we've effectively added water. Now, equilibrium generally doesn't favor the hydrate, except for the case of very simple aldehydes, and the reaction is also fairly slow, but as we talked about in the last video, we can considerably speed up the reaction in the presence of acids or bases. And so we mentioned in the last video that we can be base-catalyzed or acid-catalyzed. Well, this is the mechanism for the base-catalyzed hydration of a ketone. And other than the fact that we now have a specific nucleophile, it's exactly the same as the mechanism that we saw in the last video. Under base-catalyzed conditions, we first have nucleophilic attack, and then we have proton transfer. Under basic conditions, the nucleophile isn't actually water. Under basic conditions, because OH is present, that's a much better nucleophile than water, OH is going to be our nucleophile. And so the OH attacks our ketone, the pi bond becomes a lone pair on that oxygen, and then we finish it off with a proton transfer from a water molecule. Okay, the mechanism for acid-catalyzed hydration is very similar to the mechanism that we saw in the last video. If we're under acidic conditions, H3O plus is a much better proton donor than water, so under acidic conditions, H3O plus is going to be our proton donor. And so we're going to pick up, our ketone will pick up the hydrogen. We then follow that up with nucleophilic attack, so these steps are reversed than in the case of basic conditions. And then, as we've often seen when water acts as a nucleophile, we're adding water to something, we end up with a charged species after that step. So we need to finish it up with a proton transfer to give us a neutral compound. And so water is going to act as the base in this case to pick up that extra hydrogen atom and give us our neutral product. So these last two mechanisms involve an extremely important point for drawing mechanisms. And I think this is maybe the most important part of this video. Under acidic conditions, a mechanism is only reasonable if it avoids the use or the formation of strong bases. So if you go back and look at the mechanism for the acidic catalyzed hydration, in that last step, when we needed a base to pick up that extra proton, we didn't use hydroxide because I can't have a lot of hydroxide and hydronium ion existing at the same time in solution because they'll just react with each other. So if I have acidic conditions, I can't also have strong bases present, right? And this isn't true. This is in general true, but I think the most often time that this is going to come up is when we're dealing with water and hydronium and hydroxide. I can't have hydronium and hydroxide present at the same time. So if I'm under acidic conditions where there's a lot of hydronium present, don't use OH, right? Instead, we're going to use water as the base. And then the flip side is true. If I'm under basic conditions, meaning I have a bunch of OH minus, I can't have a lot of H3O plus floating around. And so in that case, we would use water as the proton donor. And you may have noticed, if you go back to the base catalyzed hydration, you'll see we did not use H3O plus as the proton donor. We had to use water because I can't have basic conditions and H3O plus. Now, again, I mentioned this is not specific to just OH minus and H3O plus. It's true about other acidic and basic conditions. These are the ones that just come up most often, right? But this is why I can't have Grignard reagents under acidic conditions. I wouldn't use NH2 minus as a base under acidic conditions because it can't exist with the hydronium. They'll react with each other, not react with our organic compounds.